Well, hello Internet. It's been a minute since I've made a video for you. Okay, I think that my last video was the AP Physics C um, FRQs from last year. Mechanics. I didn't do the E&M ones, and will I ever do the E&M ones? We'll find out, right? Because I don't really have time to do it nowadays. Um, so, we'll see if I ever get that out, right? But I wanted to come to you today to, of course, be able to post another video and show you what I've been working on. Something that I'm doing right now, or something that I did, and I'm not really going to do it too much going forward, is I wrote some FRQs, particularly for use in Physics C, because Physics C doesn't get a lot of love from content, right? For curriculum content, right? So I wanted to write some newer FRQs that are, I feel like that they're somewhat College Board aligned. They probably aren't super College Board aligned. These might be good to just practice off of with some more complex examples. The way that I put these together usually is by finding different types of problems, different examples of problems that we see in those classes in AP Physics C, and typically I mash up different versions of them. So you're going to see like I've got three different kinematics problems that are kind of just different offshoots of one another, and then you're going to see that I've got an energy momentum problem that combines energy and momentum into, and a little bit of kinematics all into this one kind of nightmare of a problem. I've got another energy momentum problem that's more of a kind of qualitative one, and then I've got a rotation problem that involves rotation, simple harmonic motion, and it gives you escape velocity as well. Okay. Most of these problems I've tested with students in my own classes. So these the only one I haven't is the last rotation problem and the second momentum problem, the concept one I haven't really done in Physics C, mostly because I just feel like they don't really belong in there. But I wanted to go over some of these ones that I showed, and if I can find the files, I think they're on my flash drive. I just need to go plug that in, and I can put them in here. I can share those with you too if you want to see if you want to take these problems. I know it says I'll sue you. I'm not actually going to sue you. Okay. That all that being said, let's dive in. This first problem, I call it Crota battle. Every single one of these problems has a name, and it goes in their file name. This one is called Crota battle because Crota is this guy Crota right here, son of Oryx. He is a bad guy in the game Destiny. Okay, and this is the Guardian. These are the good guys. Okay, and so this is kind of a battle with him, right? All of these problems you're going to see reference pop culture. You're going to see video games that I like, movies that I like. You're going to see there's one that references something I saw a lot of on Instagram recently, and then you're going to see there's a problem that references a pop star. Okay, let's look at this first problem. The first problem says the following problem takes place in Destiny 2, where G is equal to 10 meters per second squared. A Guardian is facing off against Crota, who stands on a platform that is 15 meters high. The Guardian hurls his throwing hammer at Crota with an initial speed of 25 meters per second and an angle of 53 degrees above the horizontal. Okay, calculate the amount of time the hammer takes to strike Crota as part A. This one comes out the gate swinging. Okay, because the way that I had in mind to solve this, and there's probably different ways that you can do this. The way that I had in mind to calculate the time directly is that you would actually have to use the quadratic formula to do so. Okay? So really quickly, the speed that I throw the projectile with, right? It should be something kind of like this. Okay, I know this is not perfectly in the line. I don't care. Okay, this is my V naught. I have an X component and a Y component. The X component of that V naught is going to be V naught cosine theta. This is going to be V naught sine theta. Okay, and I know that sine, so 53 degrees, okay, I should have more going into the sine theta component because it's going to be larger. It's going to be more vertical. So this vector is going to be more vertical than it is horizontal. So I know that sine of 53 should be 4/5, whereas the cosine of 53 should be 3/5. Okay, that comes from the formula sheet. You could put it into your calculator if you wanted to, but if you use the numbers off the formula sheet, it actually makes the problem stay with mostly whole numbers. I think this one ends up doing mostly whole numbers. So let's see, what else do I know? I know my y initial is 0. My y final is going to be 15. I know that my V naught is 25. I know that my meters per second, this is meters, okay, meters. I know that my theta is 53 degrees, okay. If I break this into components, Vx naught, the x component, is going to be 25 times 3/5. Okay, 25 times 3/5. 25 on the top cancels with 5 below, so 5 times 3, it gives me 15 meters per second. And then Vy naught is going to give me 20 meters per second. Okay. And then I know that the acceleration due to gravity is going to be 10 meters per second. You notice how I'm listing out everything that I know, right? It's technically negative 10 because it's going to go point downward, right? We throw the hammer upward, we give it an initial upward velocity, and there's going to be an acceleration due to gravity pointing downward to get it to go back to the ground. So if I set up my equation using y naught, or sorry, using y naught plus, where am I at? Y naught plus v y naught t plus 1/2 g t squared. If g is negative, this is going to, so g is negative, so this is technically going to be minus, right? So it would technically be y naught plus vy naught times t minus 1/2 g t squared, okay? This should give you y final, okay? So now I can plug in all my numbers, and I'm going to end up with a not very pretty quadratic equation. Okay, y naught is going to be 0, so I can just completely ignore that. Vy naught is going to be 20, so I get 20t minus half of g is going to be 5 t squared equals, and then the final y is 15. Okay. If I move the 15 to the other side, I can make this into something that I could use the quadratic formula on. But there's actually no need to use the quadratic formula because the factoring is really easy. Okay? If you set it up like this, again, remember, this is if you use the numbers off the formula sheet. If you don't use the numbers off the formula sheet, then you are going to end up with decimals and you are going to have a quadratic formula. Okay? If I move the 15 to the other side, I should get, and I'm going to rearrange my variables over here, right? Not yet, actually. If I move the 15 to the other side, I should get 20t minus 5t squared minus 15 equals 0. I can rearrange my variables, and so I can put negative 5t squared in the front, and then I add 20t to that, and then I subtract 15 from that, and I get 0. Okay? So I'm rearranging my variables. I'm rearranging it so that it's an ax squared plus bx plus c. Okay? And then I can factor out a negative if I wanted to, right? Actually, that's what I'm going to do. I don't like having leading negatives, so I'm actually going to pull the negative out on both sides. I can multiply both sides by -1, okay? And I should end up getting 5t squared. That should be minus 20t plus 15 equals 0, okay? I can factor out the 5 here, and I get 5 times t squared minus 4t plus 15. Plus 3, sorry. Okay. Shouldn't really be doing this in pen because I'm going to make a lot of mistakes, right? Equals 0. Now, this says that 5, obviously the 5 has been factored out, right? I divide by 5 on both sides. Okay. If I divide by 5 on both sides, I guess I don't really need to have the 5 here. Okay, I can take that out if I want to. Okay. But I'm left with t squared minus 4t plus 3 equals 0, and this can be factored, right? I've always learned it by the traditional add to get the first number, add to get the first number, multiply to get the second, right? And it looks like, right, if I multiply the two, I could do -1 and -4, okay? Or sorry, -1 and negative, let's see. So I should get t, add to get the first one, multiply to get the to get the second. Oh, so I could do -3 and -1. Okay, -3 and t minus 1. Okay, and then you'll see that your two solutions are going to be 1 and 3. Okay, and so then you would have to you would want to accept the 3 solution, and that would be something that you'd have to know in your head because first off, it's going to reach the height of 15 meters here. at t equals 1. So then it will hit right over here at t equals 3. Because that's why we're using the quadratic formula, is because it technically hits 15 meters of height 2 different times along its trajectory. Okay. Let's take a look at the next one. The next part. It says, part B says, at the instant the Guardian throws the hammer, Crota fires a bolt that travels in a straight line, okay, towards the Guardian, traveling at a constant speed of 14 meters per second. Okay, calculate the amount of time that the bolt takes to strike the Guardian. It's not entirely apparent, but since it's being traveled in a straight line, we can imply that, or we can infer that this is going to go in a straight line like that. So I need to figure out the hypotenuse of this triangle. Okay. I need to figure out the hypotenuse of this triangle. You can't really use the 53 degrees over here, okay? Because again, this isn't being launched directly at Crota. This is being launched at a parabola. But we can figure out the horizontal distance, because if we know t is equal to 3 and we know the x speed, we can figure out the distance, right? So I can say that x final is equal to vx naught times t. I know t is 3. Okay, so I can do x final is equal to vx naught, which is 15. I know t is 3. And if I calculate this out, I should get 45 meters. Okay? That's not my answer. That's my distance. Okay, that's my horizontal distance. I can then use the Pythagorean theorem to figure out the distance, the diagonal right there, right? So this is actually, if I'm not mistaken, and I actually unintentionally did this, that what happens is that this ends up, I think it's actually a Pythagorean triple if I'm not mistaken, right? Because I think it ends up being a Pythagorean triple. I can't remember exactly off the top of my head how somebody figured that out. Some kid pointed out to me that it was a Pythagorean triple. Okay, so, or you can just do Pythagorean theorem, right? You can say that the distance, I'm just going to call it d is equal to the square root of 15 squared plus 45 squared. And then that might be something that you would put into your calculator. So 15 squared plus 45 squared. And I get, okay, so it wasn't actually a Pythagorean triple. That's my bad. Okay, I thought somebody had pointed out, I think maybe it was in a different problem that somebody pointed out to me it was a Pythagorean triple. It was 45, so it was about 47.43. I rounded to about 47. I rounded to, I think it was 47.434. Okay. Meters. That's the distance. You would need to then take the speed. Okay. And you would need to say that, okay, if the speed is distance over time, so I'm going to say speed is distance over time, then I can get time by itself by flipping and multiplying distance on both sides. Okay. So I can do, if I flip it, it would give me a multiply. So it should be t is equal to d over v. Okay. And that should make sense because your meters will cancel out. So then I do, my distance is 47.434. I divide it by my velocity, which is 14. And then I would do 47.434 divided by 14, and I get 3.388 seconds about. Okay. Okay. So I get about 3.388 seconds. Okay. So it doesn't really matter how much you round on the 40, like even if you round to the whole number, I think this problem, I wrote it so that even if you round to the whole number, you're still going to get a time that's greater than the, you're still going to get a time that is greater than the amount of time it takes for the hammer to hit Crota. So Crota gets hit at 3 seconds, the bolt would hit the Guardian at 3.38 seconds, okay? Then the problem asks you to indicate which event occurs first. Does the hammer hit Crota or does the bolt strike the Guardian? You would say the hammer hits Crota. Okay? And no matter how you swing it, it's always going to hit Crota first. How can we change the answer to this part, assuming the launch speeds of both projectiles stay constant, right? One thing is, so we have to keep the launch speeds constant. Okay. One thing that we said this is pretty open-ended. You could say that Crota moves to y equals 0 to shorten length. Okay. That's one thing that that can be done is Crota. If we take him, he's up here, right? We move him down to the ground level. This distance is going to be shorter than this distance. It's slightly shorter, but it could change the result. Again, it says could change, not will change, right? So read the questions carefully. The other thing that we could say is that we could increase the launch angle of the hammer to give more flight time. This problem's not super clear, honestly, and I kind of regret putting it on there. But these are the two big things that you can do to change the answer to that part. Okay. Okay. Says now Crota now summons a thrall from the base of his platform. The thrall accelerates at a rate a over a distance x1, delta x1, then sprints towards the Guardian at a constant velocity for the remaining distance delta x2. Okay. Derive an expression for the total time t total it takes for the thrall to reach the Guardian in terms of delta x1, delta x2, and a, and fundamental constants as necessary. Notice that you can only use delta x1 and delta x2, acceleration, fundamental constants. That's pretty much just going to be g. Okay, if we end up using g. Okay. So what I need to do is I need to derive an expression for the time it takes for the thrall to go the distance delta x1. It starts at rest, okay, and then it accelerates at a rate a over a distance delta x1. Okay. So what I can say, right, is that he's going to travel a distance delta x1, okay, at rest, okay. So I'm going to say he's a distance delta x1, right? He travels the distance delta x1, and he does this with no initial velocity, right? So x naught is going to be 0. We're going to say x naught is 0. Okay, I guess you could put x if you wanted to, but the problem doesn't want us to use x, so we're just going to say it's 0. Plus v naught times t. Well, his initial speed is 0, so we're going to ignore it. Okay, and then his acceleration is a. So 1/2 at. So he's just going to be 1/2 at squared. Okay. I'm going to call this t1 because this is the time it takes for him to complete segment 1. Multiply by 2, I get 2 delta x1 equals a t1 squared. Divide by a, I get t1 squared is equal to 2 delta x1 over a, and then I square root both sides, and it's going to look super ugly, but you know what? That's fine. T1 should be equal to root 2 delta x1 over a. Okay, so there's my first segment of time. Okay, and it is in terms of the acceptable variables. Okay, that's my first segment of time. Now I need to find my second segment of time. Okay, so I can treat these as basically two separate kinematics problems. This is a starting from rest and accelerating. This is a starting at an initial speed problem, right? This is or having some initial speed and constant velocity. So it's accelerating and then constant velocity, right? So I can say delta x2 is simply equal to v. So it's going to be x naught, right? Delta x1, okay, plus v times t, okay? And there's no acceleration during this first part, okay? If you wanted to include the term for delta x1, that's fine. I actually didn't include delta x1. I don't think it would actually give you the same thing, so I would just say don't include the term for delta x1. I would say let's just treat these two pieces independently and then add them together at the end, right? So this is going to be v times t. Now this looks simple, okay? This looks simple, and you just divide v on both sides to get t2 is equal to delta x2 over v, but here's the thing. V is not permitted as per the problem. So I actually need to now solve for what V is at the end of the acceleration. Okay? So I can say that V squared is equal to V initial squared plus 2a delta x. Okay. Well, v initial is 0. Okay. Because when the first part, right, this is the speed at the end of this first segment, v initial is 0. Okay. And then 2a delta x, let's just replace delta x with delta x1. Okay. Because that's the distance that it accelerated over. Square root both sides, and you're left with v for this segment is equal to square root of 2a delta x1. Then plug that back into here, and I should get that t2 is equal to delta x2 over root 2a delta x1. And then you can plug, then all you got to do is add all these together, right? Add both of these two things together. So when I add these two together, t1 plus t2, I can get t total, and I should get root 2 delta x1 over a plus delta x2 over root 2a delta x1. Okay? And that's, oh gosh, this expression, you're thinking this is so ugly, right? But I derived it all from basic kinematics. I'm not using any calculus here. Okay? It's just moving things around, right? That's the hard part about physics. People always freak out when you get to that, but it's really not that bad. Okay? Part E says the thrall is summoned 15 meters away from the base of Crota's platform. The thrall accelerates at a constant rate of 5 meters per second until the thrall is 20 meters. So they basically are giving you values here. Identify what values are we given. Okay. 15 meters, let me actually annotate this on the diagram. 15 meters is this. Okay. We already discovered that the entire distance here is 45. Okay. 15 here. Okay. So 15 meters there is x. The thrall accelerates at a constant rate of 5 meters per second until the thrall is 20 meters from the guardian, after which the thrall sprints at a 20 meters from the guardian is this delta x2 right here. Okay. So that means that this part right here, right, is going to be 45 minus 20, which is going to be 25 minus 15. Okay. And that is going to give me 10. So this should be 10 right here. Okay. 25 plus 20 gives me 45. Boom, I did that. Okay. It gives me the acceleration, which is 5 meters per second squared. And then all I got to do now is plug all these values into the time, okay, into that expression I just derived. Okay, so let's do that, right? It's going to look so horrendous. It's not going to look very nice. But I think the number, it's not going to look pretty when we plug everything in, but I think the number actually comes out to being really, really clean, if I remember correctly. I remember I was impressed by how many of these numbers came out really nice. Delta x1, 2 times 10 over the acceleration of the thrall is 5, okay, plus delta x2 is 20 over the square root of 2 times the acceleration is 5 times delta x1, which is 10. Okay. 2 times 10 is 20 over 5 is 4. Oh my gosh, I think the numbers do come out really nicely. 2 times 10 is 20, divided by 5 gives you 4, so t total is equal to root 4 plus, and then I do 20. Okay, so root 2 times 5 is 10. 10 times 10 is 100. Square root of that is 10. This should become 2. Okay. 20 over square root of 100, which is 10. So 20 over 10 gives me 2. Square root of 4 gives me 2. So this ends up being 4 seconds. Wow, how the numbers actually did come out to be really, really nice on that one. Okay. The final question says, assume now that as soon as the thrall finishes accelerating, the guardian turns around and sprints at a speed of 12 meters per second away from the thrall. Is it possible for the thrall to eventually catch the guardian, assuming the two can sprint infinitely? Why or why not? Okay. This problem does not require you to resolve everything. It actually just requires you to know what the final velocity of the thrall is after it's finished accelerating. Okay. Well, the final velocity was given as root 2a delta x1. So if I plug in my numbers, 2 times 5 times delta x1, which we said was 20, right? No, sorry, 10. This gives me 10. It is not possible, so no, because the Guardian is going faster than the Thrall's final speed. Okay? So there's my explanation for that. Okay? All right. Can you see what I'm doing here? Right? Can you see this problem right here? Did you see this guy and you immediately were like, oh my gosh, right? All right, I wrote this problem to go off of Clash Royale. The following problem takes place in Clash Royale. Two kings are fighting from their castles, which are separated by 200 meters of both 200 meters, and both of which only need one hit to be destroyed. Castle A deploys a rocket launched from the base of their castle, which travels at a velocity of 50 meters per second at an angle of 26.5 degrees above the horizontal. Use G equals 10 meters per second squared. Guess what? It says calculate the time the rocket takes to strike the base of Castle B. This does not really, if I remember correctly, I don't think this one really actually requires the use of the range equation. Okay? Because if you know the horizontal distance and you know the initial velocity, then you can solve it. Now, the reason why the angle here is really weird is because I used the range equation to write the problem. So really quickly, right, if I know that the distance that I'm traversing is 200 meters, I know that my my V naught is going to be 50 meters per second. I know that my theta is 26.5, okay, degrees. And then I know that G is equal to 10 meters per second, but I don't think I'm going to use that for this part. I'm just going to use the X component here. I think I can just do that, right? So if I know that X is equal to Vx naught times T, because there's no acceleration in the X direction, I can just say that X is 200. Vx naught is going to be, well, I need to figure that part out, right? So if my velocity goes this way, V naught, then that means that my X component is going to be V naught cosine theta. V naught cosine theta is going to be 50 cosine 26.5. I don't know that one off the top of my head, right? So 50, let me make sure I'm in degree mode. 50 times the cosine of 26.5. And please be a nice number. No, it's not. It's 44.74. That's unfortunate. Okay, I wrote the problem poorly. 44.75. Let's round it to 44.75. Okay. And then the time is what I'm trying to solve here. Okay. If I divide this on both sides, I should find that t is going to be equal 44.75. Should be about 4.46. Okay. 4.47. Okay. Seconds. Okay. All right. Part B. What is that? Okay. Part B says the instant the rocket is fired, a prince is deployed. Okay. The prince, starting at rest, begins heading towards Castle A, accelerates at rate A for a distance delta x1, then travels the remaining distance delta x2 at constant velocity. Wait a minute. Is this not just the exact same problem? It is. Okay, I wrote it. Okay. So if you want to see that one, I did this one in the Crota battle. It should end up being that the time total is equal to, gosh, what was it? It was, I have it right here. It was the same as we did right here. It should be root 2 delta x1 over A. I add delta x2 over root 2A delta x1. Okay, so it should be the same thing. If you want to see this, right, I did this in the Crota battle part, so you can get back to that one and see exactly how I did it, because it's the exact same expression. Okay. So it's the exact same expression on that one. Okay. Okay. trying to not spoil my future problems because, like, you're not gonna be surprised, right? We're gonna be surprised. Okay, the prince is deployed 60 meters from castle B, accelerates at a constant rate of 20 meters per second squared until he reaches the midpoint between the two castles, then proceeds towards castle A at a constant rate. So let me actually write those values down on the paper. And unfortunately, these kids that got this FRQ, they did not get the diagram on the same page as the question. The midpoint of the castle is here. The midpoint between them is here. So this is going to be 100 meters. Okay. And then what does it say? It says he's deployed 60 meters from castle B. Okay. So the deployment, this X right here, is 60 meters. Okay. That means that this has to be 40. Okay. Okay. And then his acceleration is 20 meters per second squared. So you're telling me that this thrall dude here could only accelerate at 5 meters per second squared, but the prince can accelerate at 20 meters per second squared? Yeah, I don't know, honestly. I had just wrote whatever numbers worked best for this. So if I plug in my formula, right, if I say total time is equal to root 2 delta x1, right, we said earlier, is 40. Okay. Over acceleration, which is 20. Okay. Plus, and then delta x2, right, we said was 100, over the square root of 2 times a times delta x1, 2 times 20. I'm writing this really small, my bad. Times delta x1, which we said was 40. And I don't remember if this actually ends up being like a super clean number or not. I don't think it does off the top of my head. Let's see, because this right here ends up being 20, and this becomes 2, so this becomes root 4 still. Okay. And then this will be 100 over the square root of 2 times 20 is 40. 40 times 40 is 40 squared. So then I end up getting root 4 plus 100 over 40. So 2 plus 100 over 40. 100 over 40 is not going to be an even number. So I get 2.5, right? So I get is 2 plus 2.5, and I get 4.5. Okay, seconds. Okay, pretty cool, pretty easy, right? Just plugging in the same thing. What happens first? Does the rocket hit castle B, or does the prince strike the castle? Well, the prince strikes the castle at 4.5 seconds. The rocket hits at 4.47. So the rocket just barely wins this. Okay. How can I have changed the problem, assuming the launch speed of both the knight and the rocket stay constant? I could launch rocket at greater angle. Okay. To increase flight time, I could deploy prince closer to castle. Okay. To reduce distance. Okay. All right. As soon as the prince passes the midpoint, an ice spirit also at the midpoint accelerates from rest at a rate of 32 meters per second squared to catch the prince. How much time does it take for the spirit to catch the prince? Okay. So this question is kind of turning into a pursuit problem, okay, where their x positions should be equal to each other. So I'm going to say x of the spirit is equal to 1/2 times 32 times t squared. Okay. The position of the knight should be v naught times t. Okay, because he's not accelerating anymore. His v whatever after he's done accelerating, right? It should be just vt. Okay. And to find the v of the knight, I should get that it's going to be root 2 times 20 times 40. So it should be root 40 squared, which gives me 40. Okay? So the final speed of the night should be 40 meters per second. Okay? So this is going to end up being 1/2 times 32 times t squared is set equal to 40 times t. And then, boom, cancel out one of your t's on both sides. And you're left with 1/2 of 32, which, by the way, let's just simplify it. Okay? 16t equals 40. And then you can divide both sides by 16. And again, I don't think it's going to be a very pretty number if I remember correctly. I get 2.5. Wow. Oh my gosh. I am actually a genius. I might actually be a genius. Okay? Equals 2.5. Now here's the issue. When I wrote this problem, I actually wrote the last part actually doesn't have an answer. Okay? Because we know that the second segment, we know that T2 for the night, the second segment that the night goes through, is also 2.5. So what happened was I accidentally calculated, what I did was find the time that the spirit catches the prince to match it, and then I ended up writing it to conform to that. I don't know why. So really, the ice spirit, maybe you should have less acceleration or more acceleration, but the real answer is actually that both occur at the same time. Both occur at same time. Okay, so I accidentally wrote this one so it doesn't really have an answer for the last part, but you can add both occur at the same time. Okay, because they both happen 2.5 seconds after the spirit is deployed. All right, let's take a look at our next problem, which is a very exciting Alien Romulus problem. If you know me, I'm a big fan of Alien Romulus. And it's not because I'm in love with Kaylee Spaney. Okay, maybe a little bit. Okay. This is a switch up of the Crota problem, because now instead of us launching the projectile from the ground up to a cliff, it's now on a cliff and going down to the ground. The following problem takes place aboard the Renaissance space station from Alien Romulus, where g is equal to 10 meters per second squared. Rain Carradine is standing on a ledge that is 50 meters above in a room where she spots an alien xenomorph. Rain Carradine uses a launcher to fire an explosive with initial speed 25 meters per second at an angle of 37 degrees above the horizontal to hit the alien. Calculate the amount of time the explosive takes to strike the alien. Okay. What you can do is you can actually just use, I don't think this one actually requires the quadratic formula because, well, no, it does. I remember. It does require the quadratic formula because even though you're just going to end up with a solution, I think, that ends up being negative, which is kind of weird. So let's throw out what we know. We know y naught is equal to 50 meters. We know that y final is going to be equal to 0 meters. We know that v naught is equal to 25 meters per second. We know that theta is equal to 37 degrees. And then vx naught is going to be v naught cosine theta. So, and by the way, just really quickly, the sine of 37 should be 3/5. And the cosine of 37 should be 4/5. Okay. So Vx naught is going to be 25 times 4/5. Okay. Cancel out your 5 on the top and the bottom. Should give me 20 meters per second. This is just a flip-flop of the Crota problem. Vy naught will then be the 15 meters per second. Okay. And then G is equal to negative 10 meters per second squared, because it's going to be decreasing our height. So if I set up my y equation, right, my final y is equal to y naught, which is 50, plus 15t minus 1/2 times 10 times t squared. Go ahead and simplify this a little bit. Y final is 0, so it's going to be 0 equals, and I'm going to move my terms around a little bit, negative 5t squared plus 15t plus 50. Okay? I'm going to divide both sides by 5, and I should get 0 is equal to negative 5. Sorry, let's divide both sides by negative 5. And I should end up getting t squared minus 3t minus 10. Okay. You could use the quadratic formula here. Okay. But there's, I think, if I'm not mistaken, right, you can actually factor this pretty easily. Okay. I think it ends up being 5 and 2 is what it looks like, right? So add to get the first number, multiply to get the second. It looks like it's going to be negative 5. Okay, negative 5 plus negative 5 and positive 2. Okay. So I should get t minus 5 t plus 2. Okay. Equals 0. And then therefore my solutions are going to be t equals positive 5 and t equals negative 2. You would have to accept the t equals 5 solution because negative time does not exist. That implies that if we went back in time like let's say if this was a full parabola, we went back in time 2 seconds, it would be right at the floor level again. B says at the instant Rain fires the explosive, the alien spits a ball of acid that flies in a straight line towards Rain. Okay, Rain carotene. Okay. The ball of acid travels at a constant speed of 24 meters per second. Again, this is just the same kind of thing, right? Find out the x distance that the that the grenade travels, that the explosive travels. Okay. So let's see, the time was 5 seconds. The x speed is 20. So I can say x final is vx naught times t. Plug in. This is 20. This is 5. And I should get that x is equal to 100. Okay. Now I need to solve for the hypotenuse of this triangle. Okay. So if I know that this is 100, okay, maybe this was the Pythagorean triple. Maybe I was thinking, maybe this is the Pythagorean triple. I don't know if I don't think it is, but I didn't design any of these with a Pythagorean triple in mind because I wasn't thinking about, I don't ever really think about Pythagorean triples. 50 squared plus 100 squared. And then I will do 50 squared plus 100. Oh, nope, that's all in the exponent. I don't want that. That's going to be a really, really big number. Plus 100 squared. Okay, so I don't get a Pythagorean triple. It's 111.80. Okay, 0.8, I guess. So 111.8 meters. And then I just need to, again, do distance divided by velocity to get the time, right? So I can do time equal to distance over velocity. Plug it in, plug your stuff in, and it gets you 111.8 over my velocity is 24, and I get, let's find out, 4.65. Okay, about 4.65. 4.66. Okay. Seconds. This is not going to hit first. It's going to be that Rain is, or actually, no, sorry, back up. The ball of acid is actually going to hit Rain before the explosive hits the alien. So we can say the acid ball hits Rain. You know why I did that? Was because I teach on an A-day, B-day schedule. And I gave the Destiny FRQ, the Crota battle, to my A-day class, and a student told me that they knew the answer to the which one occurs first question because they knew that the Guardian was the hero of the game and the heroes always win. So I actually went and rewrote this question so that the hero does not win. Okay? So I was like, okay, you know what? I don't want you to be able to use your context clues on this one. I want you to actually solve it. How can I change my answer? Rain could launch. Rain launches at smaller angle to decrease flight time. Or you could say that, what was the other one? You could have her move to ground level. Okay. I think it was you could have her move to ground level is another solution that you could do so that she could have her move to ground level. So have Rain move to ground level. Okay. Okay. Sometime later, by the way, this is the Among Us emergency meeting button. Sometime later, the Rain again encounters the alien, but notices a button that can open the airlock and eject the alien into space, defeating it, which doesn't actually happen in the movie. Rain is initially a distance x away from the alien and accelerates at a constant rate. Okay. Accelerates at a Rain is a distance x away from the alien, accelerates at a constant rate a over a distance delta x1, then sprints the remaining distance delta x2 at constant velocity. Derive an expression for the total time. have you seen this one before? Right? Have you seen this one before? Say it all with me, right? Time total is equal to root 2 delta x1 over a plus delta x2 over root 2a delta x1. Guess what? No different than the previous times. Okay, no different. The only difference is that now Rain Carradine's running from an alien. Okay, the distance between the alien and the button is 100 meters, and Rain is initially 20. Okay, so let me label these actually on the diagram. Is initially so what does it say? Distance between the alien and the button is 100 meters, so the entire length here is 100 meters. Rain is initially 20 meters away from the alien, so this is 20. She accelerates at a rate of 1 meter per second until she is 30 meters from the button. So that's this right here. Okay, that's 50, so this has to be 50. Okay. Okay, how much time does it take for Rain to reach the button? Plug everything in. T total is equal to root 2 times delta x1, which is 50, over the acceleration, which is 1. Okay. Easy. Delta x2 is 30 over the square root of 2 times acceleration, 2 times 1, times delta x1, which is 50. What? This is the same thing, right? Whoever wrote this problem is a genius. Okay, I don't know who he is, but he's a genius. This is root 100 plus 30 over, guess what? Root 100. Okay, so this becomes 10 plus 30 over 10, which is 3. So it becomes 13 seconds, which is my lucky number. Okay. Immediately after Rain stops accelerating, the alien begins sprinting towards Rain at a constant speed of 10 meters per second. Is it possible that the alien can catch Rain before she reaches the button? Why or why not? Okay, so instead of actually explaining the whole thing, right, I'll show you the quick calculation. This part in the bottom here is the final speed of Rain. So Rain's final speed is root 2 times 1 times 50, which is 2 times 50, which is 100, which is 10 meters per second. If the alien is sprinting at a constant speed of 10 meters per second, guess what? They're not going to catch. So he's not going to catch. So alien and Rain go same speed. Okay. So the distance between the two does not change. So no, the alien does not ever catch Rain. Okay, she does not ever get caught. Okay, because she is just that much of an icon. Okay. Okay. All right. I've got a couple more because the grind don't stop. I love this one, by the way. And if you don't understand the reference that this is coming from, you need to Google it. Okay? Google electric vehicle battery ejection. I think that will get you what you're looking for. But I saw this on Instagram a lot, and it made me laugh. So of course I'm like, I'm gonna make a problem about it, right? An experimental electrical vehicle is developed in such a way that a 500 kilogram battery is stored in a compartment below the vehicle's cabin. The vehicle is equipped with a safety feature, because this is not safe, such that when a crash is detected, a mechanism applies a force to the battery defined by the function f of t, or f of t is equal to 30,000 t plus 44,000 to eject the damaged battery from the car. The experimental vehicle is initially at rest when a crash occurs, prompting the system to eject the battery. The battery is ejected at ground level and slides 70 meters across a patch of concrete where the coefficient of friction is 0.5, then slides down a frictionless incline with a height 35 meters, after which the battery slides across more concrete. At a distance 100 meters away from the base of the incline, there is a park where many children are playing. At a distance 80 meters away from the park, there is a library where many children are reading. Assuming the entire length from the bottom of the incline to the library is concrete. Assume the entire length from the bottom of the incline to the library is concrete. Also assume the park and the library to have negligible length, meaning that the park and library are exactly where they are located and do not cover any noticeable distance. Assume that the battery remains on the ground at all times. Look at all those assumptions that I'm having to say. This problem has a really complicated, like the diagram, you can get more from the diagram, honestly, from all those words, because I had to state so much stuff to be able to be like, hey, kids are going to think, like I showed this to other physics teachers and they were like, kids are going to think the battery's going to go flying off the edge. Okay, we're going to assume that it's in contact with the ground the entire time, right? The mechanism applies force to the battery over a period of 0.4 seconds. Calculate the launch speed of the battery. If I know that I have force as a function of time, I need to use momentum. Okay, I need to use momentum. So what I can do is I can say impulse, okay, is the integral of force as a function of time with respect to time. Okay? So, if I integrate this function, I will end up getting the change in momentum. I also know that change in momentum, especially if I'm starting with no momentum, is going to be equal to momentum final minus momentum initial. But if I start with no initial momentum, this doesn't matter. So that means that delta P is really equal to m times v. Okay? Okay, so when I calculate this, okay, I'm going to integrate from 0 to 0.4, because it applies over a period of 0.4 seconds, 30,000, okay, you know that old meme, 30,000, okay? You don't know what I'm talking about, Google that one too. 44,000, okay? dt, can't forget the differential term. Even though in physics we typically don't really mess with it too much. When I integrate this, I should get delta P is equal to, I'm going to divide this by 2, so this is going to become 15,000 T squared plus 4,400 T, okay? And this goes from 0 to 0.4, okay? Now, the issue with this is that this is not going to be a very pretty expression to work with, right? So you would just probably punch this into your calculator, right? 1,500 times 0.4 squared. Now, on the bright side, the 0 term is going to make this whole thing 0. So I really can just do this, okay? I really can just do 44,000. That's, I got an extra a 0 there, times 0.4. Okay, and I should get 20,000 as the change in angular momentum, or it's not angular momentum, change in momentum. Delta P is equal to 20,000. Okay. Now this is, oh gosh, what are these? Kilograms times meters per second, right? This is 20,000, right? I now need to. This is the momentum. So then what I would need to do is I need to plug it back into m to set this equal to mv and then solve for v. So I can say that 20,000 equals the mass, which is 500, times v. Divide both sides by 500. Voila. I should get 40. Okay? Don't mind the fact that my calculator is dead. It's always dead because it can't hold charge. Unlike a capacitor, capacitors can hold charge. So this is going to be V is equal to 40 meters per second. Okay? Calculate the speed at each of the following points. If the battery stops before it reaches that point, justify that using calculations. How about immediately before reaching the incline? Immediately before reaching the incline, it has friction acting on it. This now becomes an energy problem. Okay? Before reaching the incline, the battery travels 70 meters and is subject to friction. I actually need to figure out how much friction it's subject to. Okay? So I'm going to figure out how much friction. So friction is equal to normal force, which is it's a horizontal surface, so I don't need to worry too much about that. Okay, normal force times the times mu, right? So the normal force is just going to be equal to mg, right? Mass is 500 multiplied by g gives me 5,000. Mu is 0.5. So the friction force exerted on the battery should be just 2,500 newtons. Okay? So what I can do is that I can actually do energy conservation, right? Initially, it has 1/2 mv squared. At the end here, it's going to have a new speed, 1/2 mv final squared, but some of it's going to get dissipated, force of friction times distance. Okay? So I'm going to actually set up conservation of energy for this problem, right? I get 1/2 mv initial squared equals 1/2 mv final squared plus the force of friction times the distance. Okay, and I should actually know all of these values now. You could actually plug in, because if this is mg times mu mg, then you could cancel out your m's and make it maybe a little bit easier. Okay, but I just prefer to do all this. Okay, 1/2 times 500 times 40 squared equals 1/2 times 500 times v final squared, which I don't know yet, okay, plus the force of friction is 2,500, and I know the distance it acts is 70 meters. That's just before it hits the incline, okay? Let's calculate this. 0.5 times 500 times 40 squared. I get 400,000. This is going to be 250 times v final squared. And this is going to be, it's not going to be a pretty number. I don't think so. Well, it should be, right? 175,000. Okay. I need to subtract this amount of energy that we lose from the initial amount of energy that I had. So 400,000 divided by 175,000. And not divide, sorry, it should be subtract. 400,000 minus 175,000, and I get 225,000. 250 v final squared. Divide both sides by 250. Okay. So if I divide by 250, I get 900 equals v final squared. And then you don't got to be a rocket scientist to know that if you square, like what squared gives you 900, it should be 30 squared. Do you see how the numbers work out so nice? That is the work of a genius. The work of a genius. Okay. All right. Part 2 says, as the battery passes the park, round to the nearest tenth. Okay. As the battery passes the park, round to the nearest tenth. I tell you to round to the nearest tenth for a very, very important reason. It comes in later. Okay. So the battery's going to pass the park here. Okay. I actually need to figure out the speed after the incline. Okay. The speed after the incline, right? So what I can do is I can say that here, right, we know that it's going to have 1/2 mv squared plus mgh, okay? And then down here at the very bottom of the incline, it's all going to turn to 1/2 mv squared, okay? So it's kind of a two-parter a little bit, okay? I know the speed here. I'm not going to worry about the energy that was dissipated earlier, okay? And then when I get down here, it's going to have yet another new speed, 1/2 mv final squared, plus some dissipated energy. And that force of friction is actually the exact same because the coefficient was the exact same and the math hasn't changed. Okay. So as the battery passes the park, first off, I need to figure out what's the speed after it finishes the incline, right? So I should have 1/2 times 500 times the velocity, which was 30, plus the mass, which is 500, times 10, times the height, which was 35. Okay? And then I should set this equal to 1/2 times the mass, which is 500, times v squared. V final squared. Okay, I know I'm going to use a lot of v final here. Okay. Okay. I can actually cancel out my 500s in every term because there's no friction at this point. So I should get 1/2 times 900 plus 350 equals half of V final squared. Okay. If I multiply by 2 on both sides, this is going to cancel out right here. And then this will become 700. So it's 900 plus 700 equals 1/2 V, or not, sorry, there's no 1/2 anymore because I got rid of it. V final squared, and then you can square root this, right? If I add this together, it gives me 1600. So then it becomes 1600 equals V final squared. And oh my gosh, the genius is back at it again. V final is equal to 40 meters per second. Wait, so I just gained back all the speed that I lost in the initial part, right? Now that's not the speed as it passes the park, so you're not done with the problem yet. You have a little bit more to go. Because now you're doing conservation of energy from the base of the incline to here. Oh my gosh, we're like the same thing we did earlier, right? What? What? How crazy. Okay. So I already know that the initial kinetic energy that I have is going to be, right? I already know that, well, actually, I don't know what the initial kinetic energy is because I need to do that. So I'm going to do 1/2 times 500 times 40 squared. This is actually the same as we did earlier. I think we found that kinetic energy earlier. It was 400,000, right? So I'm actually just going to write 400,000. And then the final speed is going to be 1/2 mv final squared. That's what I'm trying to figure out. And then I can add to that the amount of energy dissipated, so 2,500 times the distance, which is now 100. Okay. And I forgot to replace my m right here with 500. Okay. Okay. And at this point, let's see, this is just going to become 400,000 equals 250 V final squared plus, and then this is going to become 250,000. Okay, tack on 2 zeros at the end for the 100. Okay. If I subtract, right, so I do 400,000 minus 25, or sorry, 250,000. I should get 150,000 equals 250 V final squared. Divide both sides by 250. And this is going to be V final squared is equal to 600. And this is not going to be a pretty number. That's why I asked you to round to the nearest tenth. So this is going to be the square root. Where's my square root button? Oh, no, that's squared. This is going to be the square root of 600. And you should get 24.49, which I'm going to round to 24.5. Okay, so V final is equal to 24.5 meters per second. Okay. Calculate the total distance that the battery slides. Indicate in which zone the battery finally comes to rest in. Okay. The total distance includes the distance in the first part and then down the incline, and then over the it includes the first part plus the incline plus this. We know that for a fact our answer has to at least be 70 plus 50 plus 100. So it's not going to stop in the park. We know our answer has to either be X4 or library, right? So we know it can't be any of these four. So we're already down to like a 50-50 shot on the multiple choice part. Okay. Which is pretty awesome. Okay. How do I find the total distance the battery slides? I actually just need to figure out that from this point, how long does it take to stop, right? So I can do, or where is it going to stop? Where's all the energy going to be dissipated? So it'll be 1/2 500 times 24.5 squared equals 2,500 times distance. And I need to figure out that distance, okay? 0.5 times 500 times 24.5 squared gives me this weird looking number, okay? So I should get 150,062.5 equals 2,500 times D, okay? Divide by 2,500. and I get 60.025. So distance is 60.025. Okay. This right here says that the the battery is going to travel a distance of 60.025 meters past the park, which is not enough to get it to the library. So it's going to stop actually in X4. Okay? But the total distance is going to have to be 70 plus 50 plus 100 plus the 60.025. So it would be 70 plus 50 plus 100 plus the 60.025. 70 plus 50 plus 100 plus 60.025, and I get 200, about 280. I think I accepted 280 was like the answer. I don't think we actually used the rounding or anything like that. I don't know why, but I accepted 280 as an answer. 280.025. Okay. The last question brings in some kinematics. Oh boy. Oh boy. Okay. So what I can say, right, is that the battery is badly damaged. So it says the battery is badly damaged, will detonate 7 seconds after the crash occurs. Calculate and indicate where on the battery's path the detonation occurs. Assume the incline is angled in such a way that the battery takes 1.5 seconds to slide the length x2. We also need to consider the fact that it takes 0.4 seconds for the battery to launch. Okay? So we need to figure out at what point are we going to hit 7 seconds in the, like, where is the battery at 7 seconds after the collision occurs? Okay? So we need to figure out, first off, the acceleration due to the friction. First off, you can figure out the acceleration really easily if you do F equals ma. The only force acting on it is the friction, right? And we said the friction is 2,500 equals 500 times a. So the acceleration is going to be a negative 5 meters per second squared. Okay? And at this point, you can then use kinematics to solve it. Okay, let's find t, the time it takes to go through the section T1. Okay, the time it takes to go through section 1. Okay, so you have a acceleration, right? You know the acceleration is negative 5 meters per second squared. You know the final speed. Okay, so to find T1, I'm going to say the final speed at right before it hits the incline is 30, right? So it's 30 equals 40 minus 5t. And then we should find that t is going to be equal to 2. Okay? So I'm at 0.4 plus 2 gives me 2.4. Then add 1.5. So I'm at, what is it? It's like what was I at? What did I say I was at? I can't remember. 2 seconds. 2 seconds plus the 0.4, 2.4 seconds. Add the 1.5, I get 3.9 seconds. I'm at 3.9 seconds. Okay, so this right here is 2 seconds. This right here is 1.5 seconds, right? Back up. Let's make this 2.4. And then this will be at 3.9 seconds. Okay. What about at x3? I know the speed as it gets when it passes to the park, right? So T3 is going to be the speed when it passes the park, which is 24.5. Okay. And that's going to be my initial speed is, again, 40 minus 5 times t. So if I subtract 40 on both sides, right, 24.5 minus 40 gives me negative 15.5. Divide both sides by negative 5. And I get 3.1. Okay. Oh, you can't see my math. Oh my goodness, somebody should have told me, right? Oh, wait a minute. 3.1 seconds plus 3.9 seconds gives me 7 seconds. So the battery clears X3 at 7 seconds. It literally gets out of X3 and it blows up right as soon as it gets to the park. Isn't that crazy, right? The problem was written and designed to have that sort of solution. Okay. Oh boy. Oh boy. All right. Now this problem is the one that I've looked at the least. Okay. I wrote it and I pretty much did not actually solve it. I wrote it and then I basically never looked at it ever again. This is another momentum problem. And I'm going to be completely 100% real with you here. This problem I wrote, I basically was commissioned to write it. I had a student that I don't even have ask me to write this problem, and I did it. Right, so I did it because I'm a great teacher and a great mentor to all. And I honestly, I'm gonna be real with you. I haven't looked at this, so if I completely mess this up, it's highly possible that I will. A student is driving her car of mass 1,500 kilograms and is traveling in the upward direction as seen from above at a constant speed of 20 meters per second. I'm going to label this because I need to do that. Mass of this car is 1,500 kilograms. Velocity of the car is 20 meters per second. She fails to notice a truck of mass 2,000 kilograms. Okay, so the mass right here is 2,000 kilograms, and the velocity is also 20 meters per second. Velocity is 20 meters per second. Okay. Strikes her car. The two vehicles collide. Their bumpers interlock. So this is an inelastic collision. Okay. Immediately after, oh, that means that energy is not conserved. Energy not conserved. Conserved. Okay. Immediately after the collision, the system travels at an angle with respect to the horizontal. Duh. Indicate whether the angle that the post-collision system travels at is greater than, less than, or equal to 45 degrees with respect to the horizontal. When I'm talking about the horizontal, I'm talking like this. Okay? So when they collide, right, is the direction that the post collision system is going to travel in, is it going to go at a 45 degree angle, right? So is it going to go off in the 45 degree angle like this? Is it going to go more than 45 degrees, or is it going to go less than 45 degrees, right? What's the direction, right? Well, first off, we need to recognize that the truck has more momentum. They're both going the same speed, but more mass on the truck means that more momentum is in the x direction, which means that the final system's motion is going to be more along the x direction. Okay? So we're going to say that it's going to be less than 45 degrees. Without referencing equations, I'm going to say the both cars move at the same speed, okay, but the truck has more mass, okay, so the truck has more momentum. Okay, momentum is conserved. Momentum is conserved in all collisions. Okay, so the system moves more in the x direction. Okay, and by x I mean, I just say horizontal direction. Okay, let's just say horizontal direction. Why not, right? Why not? Number 2 says indicate whether the kinetic energy of the system after the collision is greater than, less than, or equal to before the collision. Ha! Trick question. It's an inelastic collision because they stick together. So the collision is inelastic. Okay. So kinetic energy must be lost. Okay. I don't really need to explain more than that. Okay, I'm cool with that explanation. Calculate the velocity of the system after the collision. Oh boy. Okay. Again, like I said, I didn't really look at this problem all that much, so this is like I said, I'm probably gonna like massively mess this one up. Which is crazy because I wrote the problem. Calculate the velocity of the system after the collision. Now, this one was kind of I probably what should have been a little bit more clear on this problem, that momentum again is conserved in both directions, right? So the system, because you have, okay, wait, back up. I probably should have been more clear on this one. Like, this is net velocity of the system, right? So I can say the initial momentum in the x direction is going to be the mass of the truck times the velocity. So it's going to be 2,000 times 20. The momentum of the, so that should be the final momentum as well because it's conserved. The momentum in the y direction is going to be the 1,500 times 20. Okay. And then, so if I set up a conservation of momentum sort of thing, right? I can say that the, oh, sorry, that's the initial y there. This is going to be 2,000 times 20 is 40,000. 1,500 times 20 is going to be 30,000. Oh. This is the Pythagorean triple. I keep saying, I'm like, oh, this is the Pythagorean triple, right? But it's not. And then this, I think, is the Pythagorean triple because the x momentum is going to have to be conserved, right? 40,000 kg times meters per second. Then the y momentum is going to have to be 30,000 kg times meters per second. Okay. So then the net momentum is going to need to be 50,000 kg times meters per second. Let's verify that because I'm really bad with my Pythagorean triples. 30,000 squared plus 40,000 squared. And I get 50,000. Ah, I am actually a genius. Okay. So there's that. And then I have to set this equal to the final momentum, which is combined mass times velocity. So I would do 50,000 equals the combined mass of the system, which is going to be 3,500 times the velocity. So divide 3,500 by that, and I get it's about 14.29. Let's make it 14.29. Okay. Meters per second. Okay. Calculate the final kinetic energy of the system after the collision. Right. My final kinetic energy. Right. My final kinetic energy, I can actually just solve because it doesn't want me to do conservation of energy. So my final kinetic energy of the system is just going to be 1/2 the combined mass, which is 3,500, times the velocity, which is 14.29 squared. And this gives me 0.5 times 3,500 times 14.29. That's going to be squared. And I get this big number right here. Okay, 357.175 joules. Okay, I probably should have rewritten this question so that it has you do the initial kinetic energy and the amount of kinetic energy that's lost. Okay. And then after the collision, the system slides along the street. The coefficient of friction between the cars and the road is 0.055. Calculate how far the system slides before it comes to rest. So I can say that this is my initial amount of energy, 357.175. Set this equal to force of friction times the distance. Force of friction is going to be, actually, you don't really need... Well, I probably should have clarified this is a horizontal street. So the mass times gravity is 35,000. Okay. Yeah, 35,000 times mu, which is 0.55. So it's 357,357.175 equals mu, which is 0.55, m, which is 3,500, and then I'm going to multiply that by g, so it's going to be 35,000. And then the distance is what I'm trying to solve for. So let me calculate that, right? 35 times 0.55. Okay, there's that. And then I do 357, 357 divided by my answer, and I get about 18.56. Yeah, let's leave it at that. So then D ends up being 18.56 meters. Okay. Man, this problem is not great. Sorry. Okay. You can see what I was thinking with this. Now suppose the student's car is an electric vehicle. The electric vehicle is an experimental model that holds the battery in the undercarriage of the car and ejects the battery in the event of a crash. So look at what I was thinking, right? I was clearly brain rotted at this point. Suppose the battery counts for a non-negligible amount of the car's total mass and is ejected as soon as the collision occurs. All other parameters of the collision remain the same. Indicate whether the final velocity of the system in this new scenario would be greater than, less than, or equal to the final velocity of the system in the original scenario. Okay? So first off, I say that it should be greater than, because if entering the collision you have this, so initial momentum is the same, right? So I'm going to say initial momentum is the same if final mass is less, then final velocity has to be greater. Has to be. Conservation of momentum. So final velocity should be greater than. Is the final kinetic energy of the system in the new scenario going to be greater than, less than, or equal to the final kinetic energy of the system in the original scenario? Okay? It should be greater than as well, right? It should be greater than, because if the final speed increases, even though mass is decreasing, decrease in mass is going to outweigh an increase in speed. Okay? So we're going to say, I think this one actually kind of doesn't really have like a great answer. I say it should be greater than, because increase in speed is squared, while decrease in mass is not. This is a really bad question. I'm going to be real with you. I think this is a really bad question. And I did not do very good on this FRQ, so sorry about that. All right. This last one I wrote today. So, and I haven't really fully tested it yet. Okay. I was thinking about it and I was like, oh my gosh, I got to do this, right? So, if you don't know me, I'm a big fan of multiple pop stars. Lorde. You know Lorde, Claro. I'm not trying to be performative here, but Chappell Roan's one of them too. Okay. In the song Super Graphic Ultra Modern Girl, Chappell Roan references an unknown planet that we're going to assume is perfectly spherical and has a mass of 7.31 times 10 to the 22nd kilograms and a radius of 1,561 kilometers. The planet has an initial angular speed of 2.05 times 10 to the negative 5 radians per second and a gravitational field strength of 2 newtons per kilogram. In the song Good Luck Babe, Chappell Roan states that you'd have to stop the world just to stop the feeling, presumably the feeling of doing physics problems. To slow the world to a halt, Chappell Roan begins walking in a direction opposite of the planet's rotation along the equator, and the friction force that pushes Chappell Roan forward is also pushing against the planet's rotation on the planet's surface. Assume Chappell Roan to be 60 kilograms. Oh, I didn't put punctuation. Assume that this friction force is constantly applied as a foot is always on the ground at any given time. The coefficient of friction between Chappell Roan's shoes and the surface are 0.4. Calculate the magnitude of the frictional force exerted on the planet as Chappell Roan walks. I need to first figure out Chappell Roan's weight on this planet, which is not going to be mass times 10. It's going to be mass times 2. Okay? Easy calculation, right? So first off, the weight force is going to be the mass, which is 60, times gravity, which is 2. So this is going to be 120 newtons of weight. Okay? Then, if I know that, that's going to be the same as my normal force. Okay? And if I know that the friction force is equal to the normal force times mu, I'm just going to throw in 120 times 0.4, and I should get 48. 48 newtons is the frictional force that is exerted on the planet. Now, this is Newton's third law, so this is the friction force that's exerted on Chappell Roan, but she exerts it back on the planet as well because of Newton's third law. Okay? Calculate how long the frictional force must be applied to fully stop the planet. The moment of inertia of the planet is I equals 2/5 mr squared. Okay? Okay. So, let's take a look at this. Okay? Okay. Moment of inertia, shape constant of a sphere. Okay. Where's my red pen? There it is. Okay. So the important thing to understand is I can do angular impulse, right? I want my angular impulse, I want my final momentum. So my final momentum, L final, is going to be 0. L initial is going to be I times omega for the planet. I is going to be 2/5 times the mass, which is 7.31, times 10 to the 22, times the radius of the planet, which is 1,561 times 10 to the third, because it's kilograms, and I got to square that. So this is going to be some really big numbers here. And then I got to multiply it by omega. I call it omega, right? The angular speed, which is 2.05 times 10 to the negative 5. 2.05 times 10 to the negative 5. Okay? This is going to be absolutely beautiful. Okay? 0.4 times 7.31 times 10 to the 22 times 1561 times 10 to the third. This whole thing is going to be squared. And then I multiply this by 2.05 times 10 to the negative fifth. And I should get about 1.46 times 10 to the 30. Okay? So this is ultimately going to be my change in angular momentum. So ultimately my change in angular momentum is going to be, or my angular impulse is going to be 1.46 times 10 to the 30th. Okay? Oh gosh, what's the units on that? Kilograms, meters squared per second. I think it's kilogram. I think it should be kilograms times meters squared per second. Okay? Okay. Then, right, I can say that the also angular impulse is going to be equal to a torque times a time. Okay? Well, the torque, where am I going to write this? Torque is equal to R times the force exerted. We already know the force exerted is 48, and the radius is the Earth. So this is, or of the planet. So this is going to be 1561 times 10 to the third times the force, which is 48. Okay. Oh my goodness. 1561 times 10 to the third times 48. And I get this big number right here. Okay. 7492800. Okay. Newtons times meters. Okay. So there's the torque, and I can set this all equal, right? So I can say, all right, 1.46 times 10 to the 30th, right? 1.46 times 10 to the 30th equals this number, 7492800 times delta t. And I need to solve for delta t, so I'm going to divide both sides by this 749 number, okay? And it's still going to be horrendous, right? It's still going to be a really ugly number. 1.46 times 10 to the 30th over 7492800. And I'm still going to get this. This is how long that you're going to have to walk. You're going to have to walk for 1.95 22 seconds. That is a very, very long time. Delta t is equal to 1.95 times 10 to the 22 seconds. Okay? So that's a very, very long walk. Okay? That, if I want to convert it to hours, that's approximately 5 times that's approximately 5.41 times 10 to the 18 hours. Okay? If I want to convert that into days, it's 2.26 times 10 to the 17 days. Okay? So crazy, 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 crazy amount of time. Okay? If I want to convert that into years, it's about 6.18 times 10 to the 14 years that you're going to be walking. Okay? That is longer than like anybody is ever going to be alive. Part B says, in the song Super Graphic Ultra Modern Girl, Chapel Roan indicates that she's leaving the planet and you can't come. Calculate the speed required for her to escape the planet's gravitational pull. This is an escape velocity question. And if you remember, escape velocity occurs when all of your kinetic energy, or sorry, when all of your energy is kinetic. So you've got G little m big M over R of the planet is equal to 1/2 little m v squared. Little m being the mass of Chapel Roan, big M being the mass of the planet. I can cancel out my m's on both sides. And so I'm left with G big M over R is equal to 1/2 v squared. Multiplied by 2, I get 2gm over R equals v squared. Square root both sides. V is equal to root 2gm over R. Okay? And this is all in terms of the planet. I don't got to do anything with the mass of Chapel Roan, so it's fine. I will do root 2. I didn't leave myself enough space to write everything. V is equal to 2 times 6.67 times 10 to the negative 11. The mass of the planet, oh my gosh, I forgot that number already, is 7.31 times 10 to the 22. 7.31 times 10 to the 22. And then I'm dividing this by the radius of the planet, which is 1561 kilometers. So I need to convert that to meters. So 1561 times 10 to the third, and square root the entire thing. Okay. Punch that into your calculator. It's probably going to be the best way to do it. So, oh my goodness, I forgot to actually put numbers in. So I get 2 times 6.67, okay, times 10 to the negative 11 times 7.31 times 10 to the 22 over 1561 times 10 to the third. Am I good on that one? And I should get about 2,500, pretty close to 2,500, right? So if you say about 2,500, I'd be fine with that. So it's about 2499.4 meters per second. Okay, that's the speed that you would need to travel to escape. All right, here's the real hard part. Okay. Now assume that the planet is no longer rotating, has uniform density, and has no atmosphere. A hole is bored through the planet from pole to pole. Chapel Roan then jumps into the hole, and as she falls, she experiences a force of F equals negative kmr, where k is a constant. M is the mass of Chapel Roan, and r is the distance of Chapel Roan from the center of the planet. Derive an expression for the density of the planet in terms of m, r, and fundamental constants. So it has a uniform density, okay? So the density is pretty easy to figure out. What color did I use last? Green? Okay, so I'm doing purple next. Okay. Oh, I messed up. I just realized 1, 2, and then the last part is also 2. Okay, the density of the planet should be so density is mass times volume, or mass over volume. Okay. So then what I can do is the mass of the planet is just capital M. The volume of the planet is 4/3. I think it's 4/3 pi r cubed, if I'm not mistaken. Okay. And I don't really need to do much other than that. I can move this 3 up, and that gives me 3m over 4 pi r cubed. Okay. And that's perfectly fine. That's the density of the planet. Okay. 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 The last part is a little bit tricky. The next part is a little bit tricky. Okay. So it says derive an expression for the value of k in terms of m, r, capital M, capital R, and fundamental constants as appropriate. Remember that little m is the mass of where does it say up here? Is the mass of Chapel Roan, and r is the distance of Chapel Roan from the center of the planet. Okay. Okay. All right. So if my force that's being exerted here, right, is negative kmr, okay, I'm going to write that. Not be confused with moment of inertia, even though it looks kind of like moment of inertia. The force being exerted is negative kmr, okay. Okay. And then the only part that actually exerts gravitational force on Chapel at any moment in terms of R is going to be the sphere that that has her on the circumference of it, right? So I can say that the force of gravity is equal to negative g little m big M over R squared. Okay. However, it's not going to be the full. It's not going to be the full mass of the planet. It's going to be the mass that's encompassed within here, right? So I would have to set up some sort of ratio. Okay. I would have to set up some sort of ratio, right? If the density is uniform, then I would have to set up some sort of ratio for the amount of mass contained within here. So I could say something like, let's call this just M sub R, right? M sub R over the volume that is in here, right? Which would be 4/3 pi little r cubed. We should set this equal to the total mass of the planet over 4/3 pi capital R cubed. Okay. And then if I multiply this on both sides, right? So if I do M sub R is equal to capital M over 4/3 pi capital R squared, I multiply this by 4/3 pi R cubed. Oh, cubed. Sorry, my bad. Then I should notice that 4/3 is going to cancel out top and bottom. Pi cancels out top and bottom. And I will be left with the ratio MR is equal to capital M times little r cubed over big R cubed. Okay. So the M that I'm using is really just M at that radius. So instead, I'm going to set negative KMR equal to GMM over R squared using this. Okay, does that make sense? So what I'm going to do is I'm going to say negative KMR is equal to negative G little m, mass of Chapel Roan, times big M, okay, which is going to be, I'm going to put that off to the side, R squared, okay, times little r cubed. Oh, sorry. I should put big M in the top here. Okay. R cubed over big R cubed. Okay. You will notice that I can do a little bit of cancellation here, right? I can cancel out my R squared on the bottom here and cancel this out to make it into just one R on the top. I can also, if I wanted to, I could cancel out my little m's. Okay. So I can cancel out my little m's here. Oh, and would you look at that? I also can cancel out my last remaining little r that way. So I should actually find that negative k is equal to negative g, it looks like a 6, g, okay, times big M over capital R cubed. And then I can drop the negatives on both sides and say that k is equal to g big M over R cubed. Okay. Okay. And then the final part says calculate the amount of time that Chapel Roan takes to arrive at the other side of the planet. Okay. If you take a look at this is simple harmonic motion, right? We prove it. In physics C we prove it, right? And in physics C you're supposed to prove it. But the amount of time it takes for her to reach the other side, right, is going to be determined by the period of the oscillation, right? The period of the oscillation is 2 pi times root m over k, right? If I have my force function, my force is negative k little m times r, then I can actually approximate this. R is my displacement from the center, right? This part right here is my displacement. So this right here is like my x. This part right here is like my negative k, and this part is like my spring force. Okay? So I can then say that the effective spring constant is negative k times m. Okay, so I can do t is equal to 2 pi times root m over negative k times m. I don't need the negative, I can just do km. And then m on top, m on bottom, and I'm left with t is equal to 2 pi times the root 1 over k. Now, I don't want the full period, I want the half period. So this is really just going to become t equals pi root 1 over k. And if I do 1 over k, that's just going to flip this. So this is going to turn into pi times the square root of r cubed over gm. And then you can plug in your values. So t is equal to pi times the square root of, what's my r squared, radius of the planet, or sorry, radius of the planet cubed, which is like 1651, if I'm not mistaken, right? 1561. Sorry, I mixed up the numbers. So 1561 times 10 to the third, that whole thing has to be cubed, over g, which is 6.67, haha, times 10 to the negative 11, and the mass of the planet is like 7 point something, 7.31 times 10 to the 22, 7.31 times 10 to the 22. Okay, I'm not going to have room for all that stuff to write it all out, but if you actually wanted to figure out the numerical value of it, we can do that. I should get in the top here. Oh my gosh, I keep accidentally hitting enter because I keep thinking I need to hit enter to confirm I want to do a fraction. 1561 times 10 to the third, raise the whole thing to the third power over 6.67, haha, times 10 to the negative 11. I guess I don't need to put parentheses because I'm multiplying everything, so not that big of a deal, but I'm going to do it anyway because I'm a neat freak. And then 7.31 times 10 to the 22nd power, and I should get about, it takes quite a bit of time, right? It takes quite a few seconds to get there. 2,774.805 seconds. So we're just going to say the period is equal to 2774.81 seconds. Okay. Oh my gosh, we did that, right? We did that. I don't know how long this video is going to end up being because I wasn't really keeping track, but I hope you enjoyed this, and I hope you liked seeing it. So, but these are just a couple of problems that I came up with that I wanted to show off, and I hope that you gained something from it. Okay. All right. Well, I had a great time. Okay. So maybe I'll be back soon with a new upload. I'm moving later this week, so probably not for for a little bit, but yeah. All right. Well, in the meantime, have fun. Gaslight, gatekeep, girl boss. Okay. Peace out, Girl Scout.